let's go back and think about mechanical energy. If we do work in a gravitational field, how do we do work in a gravitational field? You have to lift something up, right? You have to apply a force over some distance to do that work. Once you do work on an object in a gravitational field, what does it turn into? If we lift something up in a gravitational field, we do work lifting an object in this gravitational field, it now becomes, if we do work lifting this thing up in a gravitational field, we lift it some height h, it's got a mass m, it becomes gravitational potential energy. And how do we calculate gravitational potential energy? The mass and the height and the acceleration of gravity. If we do work in an electric field, and we talked about calculating the strength of an electric field yesterday, an electric field being the space around a charged object where an electric force can be felt. So now we're going to do work in an electric field. What does that look like? Remember how we can establish a charge here? Take some object and rub it against another object, and now we're transferring charge from one to another. Well, the balloon has a net, what kind of charge? It has a net negative charge. The sweater has a net positive charge. All we did was shift electrons from here to there, but now there is a net charge on each. And you know from previous discussions that since they are oppositely charged, opposite charges will attract each other. Well, if they attract each other, there must be a force acting on them, an electric force. That means I have to apply a force to move this balloon away. But if I apply a force, moving this thing away, and I end up moving it some distance, d, if I apply a force over a distance, I have now done work. And if I do work in this electric field, that means that work turns into, we did work in a gravitational field, it turned into gravitational potential energy. We do work in an electric field, it becomes electric potential energy. And now we need to go back to our discussion yesterday about electric fields and the parallels between gravitational fields and electric fields. In a gravitational field, the amount of work we do, the amount of potential energy an object has, depends on the object itself and its mass. It depends on the strength of that gravitational field. The acceleration of gravity there describes how strong the gravitational field is, and how far we move the object is described by h. So now we're talking about doing work in an electric field on some object, and how are we going to describe the fundamental nature of the object that we are moving? It's not mass anymore. Now it's going to be how much charge it has. Q. And then we have to look at the strength of the field in which we are moving this object. What kind of field are we moving the object in? An electric field. How do you describe the strength of an electric field? E. And now if we go back to our balloon example, the distance that we move in that electric field becomes important to us. Now another way you can look at this, going back to our drawing here, the force that we apply times the distance that we move. Well, the force that we apply is the amount of charge multiplied by the strength of the electric field. This piece right here is the electric force. Most of the time, though, people don't talk very much about electric potential energy except in terms of how much potential energy is there and how much charge did you actually move. That is a term known as electric potential. It's the electric potential energy per charge. There is no mechanical equivalent to this. Picture it this way, though. Imagine you've got a 10 Newton mass, and you lift that 10 Newton mass to a height 2 meters above the table. Gravitational potential energy is the force times the distance. That's 10 newtons, 2 meters. You've done 20 joules of work. How could I increase the potential energy? For instance, double the potential energy. You might say we could double the distance, go from 2 meters to now 4 meters. Or, what else could we do? Or we could have twice as much mass up there. Both of those examples, either a 10 Newton weight 4 meters up, or 20 newtons of weight 2 meters up, both of those would have 40 joules of potential energy. But think now about what happens if we drop these. If you drop all this stuff, it's going to hit the ground at a certain speed. These two will hit the ground at the same speed as each other, but this one, when it hits the ground, will be going faster than those two. And that's what we really end up caring about when we're talking about electricity. How fast can you get a charge to move? So what we're looking at here now is not just how much electric potential energy there is, but how much electric potential energy there is compared to how much charge you are actually moving. Again, there is no mechanical equivalent to that. This is known as electric potential, and we calculate it by first calculating the electric potential energy and dividing by how much charge we moved in the first place. Didn't we just calculate electric potential energy by multiplying by the charge? And now if we divide that electric potential energy by the charge, what are we left with? We're just left with the strength of the electric field and how far you move in that electric field. The units we are going to use for calculating electric potential are volts. A couple examples for you. Your average, ordinary, everyday 1.5 volt battery has an electric potential difference You see, we talk about electric potential, the ability of a material to provide potential energy to a charge. But if you actually want to get that charge to move, you have to have a difference between one side and the other. It has potential, but you can only use that potential if there is a difference between this side and that side. Even the negative side on a battery has electric potential. It's just got 1.5 volts less electric potential than the positive side of the battery. Your average, ordinary, everyday 9-volt battery, same thing. In fact, it is exactly the same. In this little 9-volt battery, there are actually 6 1.5-volt batteries linked together in series, so that between one side and the other side, all 6 of them together provide 9.5 volts of electric potential energy per charge that they are moving. So you've got the positive side, the negative side, 9.5 volts of potential difference. There's still electric potential on the negative side, but there's 9 volts more potential on the positive side. Your average, ordinary, everyday plug. What is the potential difference between one side of the plug and the other side of the plug? 120 volts. Between one side of the battery and the other side of the battery, there's 120 volts of potential difference. There is still potential on one side, but 120 volts more potential on the other side. Let's do a couple examples. Number 2. A charge moves a distance of 2.1 centimeters in the direction of a uniform electric field having a magnitude of 225 newtons per coulomb. What kinds of things are we given here? That's a distance. What do you have to be careful of with that distance? We're looking at the wrong units for all the calculations we have ever done, so we've got to do a unit conversion on that. What else is given to us? And newtons per coulomb represents the strength of the electric field. 109.7 times 10 to the minus 19. That J stands for joules. So this is the work we've done, but specifically it's work in an electric field. Therefore, it is electric potential energy. And we are trying to find the magnitude of the charge. So, electric potential energy equals the charge times the electric field times the distance. We're solving for Q. How do you get E and D over there? So Q equals electric potential energy divided by the electric field times the distance. Now a caution about my notation. I've been using these capital E, P, E to represent electric potential energy. Other people we'll use other abbreviations for electric potential energy. You need to recognize that none of these E's on the top can cancel with that E on the bottom. They represent totally different things. These go together representing one quantity, electric potential energy. This is the strength of the electric field. They're not the same. Number 3, an ion. That's a charged particle is displaced through a potential difference of 61 volts and experiences an increase of electric potential energy. Calculate the charge on the ion. 61 volts represents the potential difference, V. Electric potential energy is given to us. And we're looking for the charge again. Potential difference equals EPE divided by the charge. So Q equals EPE divided by V.